Hello and welcome to the Global Business of Data Festival. I hope you have been enjoying the morning content. My name is Catherine King and I'm the Head of Digital Content and Community here at Crinium. We do so hope you've been enjoying the morning, which saw us taking a trip around the world, chatting to a diverse set of leaders. And now we're excited to kick off our regional content. Up first is a brilliant presentation session all about self-driving telecom. Now remember, the afternoon is live, so you can submit your questions via the Q&A tab on the right-hand side of your screen, and it will be my pleasure to ask them to our amazing speakers and guests across the afternoon. Now, without further ado, it is my pleasure to welcome to the virtual stage the wonderful David, who's the Chief Data Scientist for Blue Planet Division in Siena. David, I'll hand it over to you.
Yes, thanks, Catherine, and hi, everybody. And just first, quick technical check. You can see can you see my slides very clear?
We sure can. Take it away.
Yes, so today is my pleasure to tell you about self-driving telecommunications network, which is, a next frontier of AI for sure. So I'm David Cote, yes, Chief Data Scientist for Blue Planet Division of Siena and in the telecommunications industry. So today my talk will be split in two parts. So I will spend a good chunk of time for this audience that I assume you are not so familiar maybe with telecoms, right? So I'll explain first why telecommunications is a thriving new field for AI. That is really ramping up at the moment. And then, but in general, not specifically about, the work that I do with my colleagues at Siena. And then the second part will be about specifically about the steps we're taking towards self-driving telecommunications networks at Siena. So then the first part. When we think of AI nowadays, there are a few domains where AI is very mature, has been, very successful, has been proven to work. And even in some cases have been proven to achieve superhuman performance. So with AI, in general, you can do two things. One is you can automate. You can use artificial intelligence to automate something that humans can do with their natural intelligence. But not necessarily do better. But then ideally, you can even not only automate, but do better. This is what I mean by superhuman. This is very exciting, of course. So yeah, when we think about these mature fields, right, on the left is when we use supervised machine learning, which is essentially learning from examples. You show lots and lots of examples of what you want the computer to learn, and it does learn. So if we think about, then we think computer vision, natural language, these fields are very advanced. And as a matter of fact, since 2015, in computer vision, you can use now, deep learning, deep convolutional neural networks to classify images even better than humans can do. So that's on the left. And then on the right, a few years, even more recently, there is another technique called reinforcement learning, which is learning by trial and error. And this also is very exciting. This type of technology is used for self-driving cars, but is also used for games. So, for example, the Chinese game of Go, maybe you have heard about this AlphaGo Zero prototype that was developed by Google DeepMind, where you basically have two computers, you just tell them the rules of Go and you let them play millions of games against each other, and eventually they become so good at the game, they, get much, much better. In fact, they're the best human Go players in the world. So this type of result is very powerful and inspiring. So for us in the telecoms, we're basically catching up and taking inspirations from these. Yeah, if I take one more step back, from an historical perspective, again, try to put my topic in context, right? So here is my take in a nutshell on history of machine learning coupled with history of telecoms. So I don't know, maybe some of you will be surprised to know that, in fact, all the main machine learning algorithms, they have been invented a long time ago, as early as in the 1950s. However, at the time, the computers were not powerful enough, and there was not enough training data. So machine learning was more academic curiosity at the time, but not real-world application. In terms of telecom, I mean, I don't trace back the full history, but one thing major that happened in the 90s is the internet, becoming widely available to the broad public. And then the next decade, another major improvement is the rise of big data technologies, such that, since the 2010-ish, right? Not only AI can achieve superhuman performance in, I will say, controlled experiments, but also AI and machine learning have been proven to be hugely profitable in the real world for industry, with the likes of Google, Facebook, Amazon, and several others. This has shown to the world that, machine learning is a thing. It changes the world, and it's profitable. It can be. And then in the network, in telecom, at the past decade, also something very important happened is that the telecommunication networks, they started to become, initially, they were hardware. You have your routers and your switches, and they're connected with physical wires or maybe optical fibers. But you need humans to configure them, and even touching physically the cables and so on. But now, since more than a decade, we have this paradigm of software-defined networking. So we can now, all the networking equipment has interfaces and you can connect to it remotely with a computer, and so you can control the network with software remotely. And not only that, a lot of the networking infrastructure by now can be virtualized. So you can have virtual machines. You can put them in the cloud, even having virtual networks, in big data centers. So that, opens up the door for a lot. This then makes it a very rich playground for optimization, automation, and AI. And then, if I go to the present tense, two major things now happen. One is in the 5G cellular networks are ramping up, and these have unprecedented levels of virtualization and complexity, but also huge potential value and huge new possibilities, but coming with complexities. And we have the first AI-assisted, networks going in production. So the prototypes that were developed in the 2010s now are in production for the first generation. This is very exciting. So now, when I talk about AI-assisted network operations, right, what do I mean? Well, so this is a cartoon that illustrates what I mean. So at the bottom here, you see the network. This is literally thousands of pieces of equipment and services all interconnected. And then we have here the network operation. NOC is for Network Operations Center. So in there you have teams of people, tens, hundreds for the largest networks of people. And their job is keep the network up and running 24/7 So they look at screens, and basically there is a continuously coming flow of performance monitoring of the network and also alarms. But there are lots of alarms, and not all alarms are equal, right? Some are just warnings, some are very serious critical events that you must react immediately. But this is it's not obvious what is which, and it's also here this flow of data is in fact big data. But these people in the network operations center, they have a lot of expertise. They know collectively how to fix everything. They know what is important, what is not important. So the goal with machine learning and AI is to capture their collective know-how by, basically figuring what is the right data sets to look at and learning from it. And yeah, so and one thing that important thing I don't want to forget to say is that in the knock, when they find something important needs an action, well, they do take an action. Typically they open one or several tickets, and they go on and they take remedial actions that get down to the network and close the loop, if you want, and fix the problem. So when we say now, so this is the concept. Now, when we say machine learning, we need data, right? So what is our data? Well, I mentioned some of it already, but it's basically these alarms, performance monitoring, and for all the services, what's the quality of service, and and also when there are config change, remedial actions, right? Then there are logs, that the event logs, and the configuration files, and finally the graph of how things are connected with each other. So this is our global data set in telecom, with the high level goals of, yes, automating and optimizing their network operations as much as possible, and of course ultimately maximizing the quality of experience of the end users of the network. So I mentioned 5G networks, right? So this is now a fact that 5G networks, compared to, because telecom networks existed in the 70s, the 80s, 90s, and now with the 5G, but it's basically like the picture here, right? Initially you had, a small network, which became, nationwide and worldwide, but still kind of fixed. And now it exploded with Internet of Things, 5G, and all that. The cellular, everybody is connected with cell phones and all the virtualization and so on and so forth. So the modern networks are, incredibly powerful, incredibly flexible, which is awesome, but also, yes, more complex. And so with the 5G now, I argue that AI-based automated network assurance is in fact necessary, is not even good to have anymore. And I put at the bottom a link to a blog where we explain our point of view in more details here. But yeah, more specifically, a 5G network, looks like this diagram here, and you have all these actions here that you have to do, and you could in principle do this manually with expert humans, but it will cost you a lot, right, to have all these people. So if you can automate and do it with an AI, or in general software, right? This is good. So at Sienna, now this all this problematic that I have introduced, this is how we address it. So we have 3 pillars for the network end state. So at the bottom is the programmable infrastructure. So these are your routers and your switches and your your networking infrastructure itself. But as I mentioned, it is now programmable. It has an API, and it exposes the knobs that you can adjust remotely. And to adjust these knobs remotely, then we have more and more a substantial and sophisticated layer of software on top to control the network and automate the network operations. So with just the software and the programmable infrastructure, now it's like you have, if it's a car, like a car, right? You're on the steering wheel, but you have so many buttons and things. So you can do everything or anything. However, you should not do everything and anything there. You don't. But bottom line is with the software and the infrastructure programmable, you can do anything, but this doesn't tell you what to do. You don't know what to do. To know what to do when, such that you run your network optimally, right? Then this is where you need your layer, your third pillar, which is analytics and intelligence. And specifically, I'm converging on self-driving networks, right? So when we're talking about driving the network, we're not only passively observing what is going on and looking for patterns, which is one thing we can do with AI, but we're also explicitly sending instructions to this control software to change the network and have a fully closed loop like this. This is self-driving network. And the key and one and last key AI concept that is, widely successful in the industry in general, and that applies here in particular for telecom, is a recommender engine. So we want the AI to recommend to the control, hey, I recommend you go on and change the routing for this service, or I recommend you go on and reboot this cellular tower, and so on. So yeah, this is last generic concept here, recommender engine, but for network operators. So, Amazon, I think, has been arguably the first one to be commercially very successful with a recommender engine that basically says, if you liked, you purchase these products, and then you probably would be interested by these others. And it is accurate, right? And you see the other companies also have powerful recommender engines, and so this is literally what I'm working on with my colleagues now, to where the story is have a recommender engine for the network operators. And so this is my segue then to specifically what I do myself with my colleagues about a self-driving telecom network. So a self-driving telecom network is a network where this full loop is automated and runs by itself. So if I get back to AI-assisted network operations, and I showed this cartoon before, in practice, then to have a self-driving network, there are 5 steps that you need to implement. And today I don't have time to explain all the 5 steps, but I can tell the first 4 steps are all available in commercial products today, even though they all have a roadmap to continuously improve. They will continue to improve for several years. And the last one is about the actual closing the loop. This is the right now prototype, but it's coming as a commercial product soon. But yeah, in a nutshell, first we need to discover what's in the network, what is connected to what, and then we need to start collecting data from all this equipment. And notably, we can detect anomalies. We can also forecast trends. And then I mentioned here, there's a huge flow of alarms and also of anomalies in the performance monitoring time series. But we don't want the network the NOC people to look at every alarm, because it's a huge waste of their time. Only a small subset needs their attention, needs an actual remediation action. So we want to learn to rank the alarms and prioritize the ones that are important. And then once we've identified these important alarms we want to know, then we want to help these people in the NOC to troubleshoot faster. And so, because to know how to fix a certain alarm, you need to know what is the root cause for it, and then go and fix it, right? So automatically determine, run diagnostics, determine the root cause, and then, yes, recommend remediation action, and eventually close the loop and do the whole thing automatically. Today, I will focus only on just 2 of the items. in the interest of time, and maybe also depending who you are in the audience, you maybe don't even want to know all the gory details of all this. But yeah, so still I showed how to prioritize important alarms using AI, and then how to recommend the remediation action for these important alarms. So I jumped to step 3, right? Prioritize important alarms. So here, this is one very nice success story of using AI for the telecom domain. Because the problem, as I mentioned, is only a small minority of the alarms actually require remediation action from humans in the network operations center. So they waste a huge amount of time by looking at all the alarms. So the solution is we want to rank the important alarms and put them on the UI at the top of the list. However, for this, traditionally we can try to use rules. If you see this, if you see this KPI crossing some threshold, and if you see this alarm for this specific device of this vendor in this circumstance, then it's important, so put it at the top. And this works, but it requires a lot of expertise to develop these rules, and also these rules are very fragile. They work on the day they're deployed, but then the networks evolve and change continuously, and there are new vendors and new equipment and new upgrades, and then it's very hard to maintain. So now, well, still these rules have value, but what we do now, we add to this a new AI layer. And the solution here is that, we want to predict which alarms will require an action. Well, fine, we just collect the necessary data and we'll accumulate for enough time. And then we see historically in the past 6 months which alarms have, the NOC has acted on, right? By clicking on our UI, by creating tickets, and by taking remedial actions, right? So then we get to the right. So then basically the more our system gets used, the more our system learns what is important for the user, what needs their attention. And so on the right, this is the result we get in the real world, a large network. And you see in the whole circle is all the alarms, which over 6 months adds up to around 2.5 million alarms that people needed to look at. Now with the built-in expert rules, we could suppress already the green circle here, which is, a nice 30% suppressed. But as they use our system, we learn this blue circle. So a whole bunch of additional alarms have been figured out. You know what? This can also be ignored safely. And this is especially powerful because here you have, about 90 different types of devices, and it's from all types of vendors and technologies. But our AI we don't need experts for all of this. We just learn from the users interacting with the system. So that is a nice success story. And then, I go to the last step, which is, okay, now how do we fix these alarms? And now I wanted to show the most exciting results. So we are working with our customers in the real world, in the field, on this remediation action problem. But also we have a test network. And actually, we do have a self-driving network prototype in Siena in our lab today. So we have we do have a network. We break the network on purpose, and then we are mocking that there is a NOC, network operations center, taking actions to fix the problems, right? So then here we do use both supervised machine learning and reinforcement learning. And here, if I start with supervised machine learning, what we can do is we can basically learn the expertise and the rules, implicit rules of the NOC actions. So you can see here, the x-axis is time, the y-axis is what we want to maximize. So basically, the higher, the better. And this is, so it is effectively, we want to maximize the quality of experience of the end users of the network. So here what we do is we're playing videos continuously across the network. We measure the quality of experience of these videos. But at the same time, we want to minimize the operational cost of the network. We don't want to give, crazy high bandwidth to every single video all the time, because this is expensive. So we want to maximize quality of experience while minimizing operational cost. We tune in. So if there is no expert rules closing these loops, we get the black curve, because these problems, get fixed eventually, but it takes a lot of time. If we have the expert rules in the automatic closed loop, then we get the blue curve. So it's already much better than the black curve, but this is based on these expert rules that are hard to maintain. But yeah, then the result in the green curve is with supervised machine learning, just based on data, without coding any such rule, we can learn effectively the equivalent of the rules and automate it without needing humans to in the loop. And then with reinforcement learning, not only that, but you see now with the blue curve is what we get with reinforcement learning. Again, the higher the better. So we can even learn that. Then the AI can learn even new rules of its own, and that do even better than the experts. So which is the ultimate goal, and which is so in our lab we have a superhuman network operator running a prototype self-driving network. So which is the holy grail, and now we're working on progressively deploying that in production. So I'll skip that slide and just show my last analogy, which is with self-driving cars. So the thing with a self-driving car is you do want to automate it, but you'd never want to crash a car, obviously. So then in the self-driving cars, in this industry, they have, in fact, 6 steps of automation that are standardized, and you can read it on the slide. So, but it's a step-by-step process. It's not everything automated from day one. And it's exactly the same with telecom networks. Telecom networks are mission-critical systems. We never want to crash them. We want to automate them, but we want to play safe. So we go step by step. For example, first step is recommend to a human, yeah, you should probably take this action, but not do it automatically. Let the human do it. But as we build confidence in the system, we can close these loops for more and more and more situations. And so that's it, right? Telecom is a thriving new field for AI. Very exciting to be in there at the moment. Several AI applications are now deployed in production. And self-driving telecom networks are not yet in production. I mean, not fully automated at least, but they are on the horizon. And they are one of the next frontiers of AI. And that's it. Thank you.
Absolutely incredible, David. Thank you so much. To the 30-second mark as well. So thank you for keeping time so well. Absolute pleasure to have you. Unfortunately, we don't have time for questions. So if you do have any questions, please do connect with David both on LinkedIn, but also in the internal platform here. We have a direct messaging service. Already, David, you're receiving comments here in the chat congratulating you on such a great presentation. So thank you. Now, we will be moving to our next session, where we will be joined by a thought leader to discuss balancing the safety and utility of data. We'll see you over there.
Thank you. Bye.